Okay, so we're going to go over how we draw the shear and force bending diagrams. So first you have to draw the free body diagram that you get from your page, right? Whatever. You get your page, whatever. You draw it, and you make cuts in between each of the forces. Ideally, you'd make 2 in between the first 2 forces, but it really doesn't matter here. You can. It helps a lot. But, do 1, 2 cuts, and then cut, 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 whatever. Then you're going to find the forces, the sum of forces and the sum of moments based off of this diagram right here. So you find so we basically use AY minus 6 minus 12 plus EY minus 4.5, and we have that right here. But we have 2 unknown variables. So when we take the sum of the moments, we can find EY with this algebra, because you take the sum of the moments based off of A, which makes us cancel A and only focus on these. So we find out that EY is equal to 16, and plugging that into the sum of the forces, we get that AY is equal to 6.5. So by doing that, we find out the values, and with these values, we actually use them right here. So we base the shear and bending diagram off of this model only. We don't get the numbers, but we get the models. So what we do first is we take AY, the value of AY. I have actually already drawn another one here, and this is going to be AY. The first thing you draw is going to be AY, the first force you have. So since we know that AY is 6.5, we're going to draw up 6.5 because it's positive 6.5, and we're going to draw a line, okay? And then to the next one, we have 6 kips going down. So we come right down to 6. 6.5 minus 6 is 0.5, so we still have that little sliver right here, okay? And then our next force is 12 kips, minus 12 kips, so it goes down again. And then we have a positive EY, which we know is 16. So over here, we come and we go up 16. And then on the last one, we have a negative 4.5 kips. So we come over here, and we go down 4.5 kips. And it will, if we do the math right, it will always end up on the line because it ends up at 0. Okay? And so the bending diagram is the exact same. It's based off of this. So what we're really going to do is we're going to see from here to here, it's going up, and it goes up, right? So this is going to match this. So realistically, it's supposed to be drawn in parallel, but it's not right now. So then it goes down and down. So from here, or basically from here to here, it is negative. So we go from here to here, it is negative. So it goes down all the way. And then it goes up. And what it goes up should be the 4.5 kips or whatever, but it goes up and it matches to 0. It always ends up at 0. So the bending diagram is based off of the shear diagram. If we're positive, this thing's going up. If we're negative, this thing's going down. As long as we're going down, it doesn't matter at what distance. This will go down in one line. And since this is positive again, we go positive. So it ends up at 0. Now, the math part is the actual hard part. So what we're going to do is we're going to get little cuts of these little sections right here. So we're going to get the AY, and then V1 and moment 1. So this V1, I don't know what it's for, but you need this force because it goes down. So we get the sum of the forces of Y, and then it ends up being AY is equal to V1. So V1 is 6.5 because AY is 6.5. The moments here are equal to 0 because M1 equals 0 is 0. So on the next one, we make the next cut. We include the 6. Okay, so we get the forces, the sum of the forces, we get 6.5 minus 6, okay? And then we get the value of V2 from that. Then, using that value, we plug it into the sum of the moments based on naught. And naught is always going to be this little beginning part of each little cube, of each little rectangle. Always is going to be based there. So what we do is we get that, and we end up using the sum of the moments. So the sum of the moments, we have the value of 6 here, so negative 6, and it's 2 away. And that 2, we got it from up here because the 6 is 2 away. So we're going to use the V3, and the V2 is going to be the exact same distance because it's on that edge. So we're going to include the moment of V2, which we know is 0.5, so plug it in, and then the distance is 2. So that's the moment from V2. And then we plug in the moment, the M2 variable. So and realistically, all we're looking for is M2. So we get M2, we equal it to 12 plus 0.5 times 2, which is the V2, and we get the moment for that section. And we do the exact same thing over again here. Again, here we do it basically in the middle or in between, like between the two forces. But what you really want to do is right before you make the cut right here, right before you get into the next force. It's not on the force, so it doesn't include it, but it's right there. So the distance is the same. So the force that goes here for the V3 is going to be 2 plus 2, which is 4. as if it were the 12 kips, but it's not 12 kips. So we're going to do over here the same thing. V3 is going to be 4 away. So we're going to do the sum of the forces first. We're going to do 6.5, which is from the A1, the AY. 6.5 minus 6, that's from here. And then minus V3. Okay, so we have it all in order. And then we're going to do it again. So we found the V3, and then we're going to put it in the moments. And it's the exact same thing. But however, the 0.5 that V3 is equal to, this little thing right here, this distance is now 4 because the cut is right here, right before the 12 kips. So 2 plus 4, 2 plus 2 is 4, but it's not 12 kips. So then we're going to go down here, blah, blah, and then we're going to get the moment because M3, right? We always have that M3 value in the moments, in the sum of the moments. And now we're doing this on every single one. On every single little cut, we're doing the exact same thing until we reach the maximum moment, which eventually is reached here at 14 kips on in between, like right after the 12 kips, right here. And we find the minimum, which is -9, right after the EY. So on this thing, we can find the maximum and the minimum. Since they didn't ask us for the minimum, we don't really need it. It's like an extra. But they did ask us for the absolute value of the maximum. So where that goes is the bending diagram. So we know that this value is 14 because that's the moment we got right here. That's the maximum moment we got after doing all those cubes. Again, this is right after this one that we just did. We just went over. It's going to be the exact same. So again, we take the sum of the forces, 6.5 minus 6 minus 12 minus V4, right? And we find out V4. We solve for V4. We find out it's -11.5. And then we take the moments, the sum of the moments. So we cross out this one, and then we do moment of 6, moment of 12, moment of V4, and then moment of 4. And again, V4 is in where the 12 kips is, right? Because the 12 kips is on this. So we're going to go back here, and where's 12 kips? 2 plus 2, it's at 4. The distance is 4. So for this, it's going to be the exact same distance. It's going to be the 4 and the 4 for the 12 kips and for the V4 because they're in the same place. And then you find, with that, you find the moment 4, which ends up being the maximum. So the maximum of this bending diagram is 14. The minimum is 9, but they're not asking for the minimum. So again, if they don't ask you for an absolute value of this, like they do on this question, where they do right here, the absolute values of the shear and bending moment, we can find that because we did the math here. We can find that of the shear diagram. But to find the values of the bending one, we have to do this math. So if it only asks for the shear and bending diagrams, we can make those based off of this, just the free body diagram. But if it doesn't ask for them, like that's all you have to do. But if it does ask for those, maximums that we needed, you have to do this math where you cut it and you use your little blocks. So that's really all there is to it.